one in Paris and the other one in Brussels, and you may have heard of his experiment on talking heads. Today he will talk about multi-agent models of category formation. Thank you.
Well, thank you very much, and thank to Kimberly and Dawn and the organizers and Janet for inviting me here. It's really wonderful, great talks, and great interesting work. So I'm coming from, let's say, AI, robotics, computer science angle, although my first training was in linguistics. And so this workshop is about the evolution of psychological categories, right? And so I guess we all agree that categories are about how you carve up reality, virtual or real. We have perceptual categories, colors, sounds, spatial relations, all that. But we also have linguistic categories, and maybe if I have time, I will come to that as well. Now, this workshop is about the evolution of those categories, and I guess there's two meanings to this word. One is, where does the machinery for doing categorization comes from, and how did it evolve? And I don't think we're really talking about that in this workshop, but rather, where do the categories themselves come from? And the color categories and the spatial relations and the phonetic distinctions and all of those kinds of things. And so this is also what I will focus on. Now, just to summarize the debate, I'm sorry if this is all old hat, but there's sort of, for centuries, discussion about three different positions. And the one is that those categories that we employ, they're somehow genetically determined. I think a surprising number of people believe that. And particularly in linguistics, I think most linguists believe that a lot of categories are innate. And if this is the case, then they evolve by natural selection. Then you have many evolutionary psychologists worrying about how that could happen. There's the other position is about that categories are induced from data, and we heard already some talks about this taking this particular angle. And of course, you have intermediate positions where you say, well, what's genetically determined is the bias in your learning, for example. And so there's sort of lots of mixtures between them. Now, there's a third position, which is maybe not so common, but which is that categories are postulated. I mean, they are kind of invented, you might say. And then they are tested against reality for whether they satisfy the functions that you want. So this is a sort of functionalist viewpoint or a selectionist viewpoint. An example is that if you have to put your clothes in drawers, and the question is where do you put what, right? And so, well, you need some sort of categorization where you're going to put things. And if you go in people's homes, then you find that this can be very bizarre. So like this can be winter, summer, spring or something. Well, in California, you don't have that much distinction, but in
summer, and summer.
Yeah, right. Or it could be the old clothes or new clothes, or the children, the parents, whatever. But they're sometimes very funny, or the colors, or it can be anything, right? So we construct categories and then we use them. And if we live in a household, then the idea is, of course, that we all use the same categories, right? And a lot of conflicts in families appear because there's people don't follow the categorization, which the other ones thought should be there, that kind of thing. So this is a sort of constructivist attitude or approach, and I sort of lean towards a constructionist view, particularly for linguistic categories. Okay, now, there's a certain number of facts which we already heard here. So the first one is that there's clearly trends in human categorization. And I think the talk we heard in the beginning is really about that. But there's not only clear trends, but there's also clear variation. And there's variation between different groups. So if you take the Berimo color categories and you take the English and you compare them, you see differences. And also between different individuals, even if they are within the same group. This was not so much emphasized, but you have papers clearly showing that. And also, we shouldn't, there is plenty of evidence for long-term cultural change. For example, in English, the color terms, well, were not hue-based until, I think, 12th or 13th century or something like that. So they were based on brightness distinctions. And there's also a lot of evidence that there's short-term rapid alignment within a dialogue. So the idea that we have a fixed system of categories that then we learn and then doesn't change anymore is just fiction. We change our categories all the time, in fact, and sometimes very quickly. Now, Terry also talked about vowels, you know, and this is indeed, we find the trends in vowel systems. So these are typical examples of 6 vowel systems. Some languages have 3, 4, 5, 6, 7, etc. French has a lot of different vowels. For example, you have a difference between le, e, these are all different vowels, and they are different meanings. You know, when you say le, le, etc. So some languages have more, some have less. And if you start talking to, let's say, if I'm in Australia for a while, then after some time, you know, there are certain Australian sounds that start to appear, whether I like it or not. So we adjust. We are kind of social chameleons. We cannot help but that our categories and distinctions are adapted all the time. So I'm sort of arguing for, you know, we have to look at the dynamics of the whole thing, not just in the speech, but also in the grammar. Most people seem to think that grammar is rather static, but in fact it's moving all the time. And this is an example from investigations of 2 construction grammarians, Zwicky and Michaelis, of the is construction, which for me at least, is very bizarre. Now, you all know it and you use it, yes, of course. Well, when I saw this, I was a little bit shocked. Of course, I'm not a native speaker of English, you know. So it's that doubling of the is, and there's plenty of examples, and they traced it. This is a recent development in English. So and they try to explain where it's coming from, and so this is it doesn't happen over centuries, and it doesn't happen, I should say, over generations. There's a very strong emphasis in all the talks we heard about this kind of iterated learning, but actually work of Croft, for example, and many other studies have shown that the innovation in language does not happen by the children. It happens by the adults who are modulating, shaping, changing their language in order to solve problems in communication. And then they propagate in the population. And so if you're a child, of course, you do a lot of innovation. You invent new words and new grammatical constructions, but you don't have the influence to actually see it propagate in the language. Anyway, so this is all puzzling, right? How do we explain, on the one hand, that there are all these trends? And then how do we explain variations like a paradox? And so each of these different views has their own approach on this problem. And I sort of think that none of them is really satisfactory. You know, if you say, well, like in phonetics, why do we have this particular trend in the vowel systems of the world? It's because we have these genes that set these particular phonetic distinctive categories and all that. Okay, fine, but then where's this variation coming from? You know, is it genetic variation? But then it's between populations, right? Between, let's say, French and English speakers. And, well, is that based on genetics? I mean, that sounds funny, right? And so I think that at least the thing that I'm going to try and argue today is the following, that we need something more. And so the something more is the following, that I'm going to assume that every individual builds their own categorical inventories, okay, driven by need. So this is a bit of a constructionist point of view, but I mean, if you are more into learning, that is fine too. The thing is that there must be something like an invisible hand that coordinates categories across individuals. And this is what I like to understand. Well, I want to understand this, where new categories are coming from. And then this coordination process. And then when we get this into motion, then the idea is that the inventories will never be completely equal. If you do tests, you will see that. Careful tests like color naming tests and so on. But they're just sufficient for cooperation and sufficient for communication. Okay? And moreover, I'm going to expect that the categories are constantly adapting to cope with changing needs. So if you have a color, an inventory of color categories, and then, you become a painter or you start working in a textile industry or you're a fashion designer or something like that, you get more refined language, more refined distinctions, as you need it. Or if you start working in the perfume industry, then your smell categories will have to become more refined, or in the wine industry. Okay, now how am I investigating this with my, my students and so on? Well, you could either do it in an empirical way. We are not doing that. But there's work, for example, by Bruno Galantucci on this. And so this is, you take humans, you put them in a situation where they have to invent a new communication system and new categories also to go with it. And then you see how well they're doing. And I think these are fascinating experiments which show that people are indeed able to do it. You have pairs that are interacting and that are quickly arriving at the communication system for their task, but some are not able to do it, which is also very interesting, or they spend hours and hours, they don't get it. That's not what we are doing. What we are doing in our lab is to do experiments with artificial agents that are cooperating in some task. The simplest task would be that one draws the attention of the other to some object in the world. And so they are cooperating, and symbolic communication is potentially useful. It's not necessary. They can point or they can do other kinds of things, but it's potentially useful. And what we want is that the communication system emerges without human interaction. So there's no example from which they can learn. Both the linguistic system, the lexicon, the grammar, and the categories that are expressed by the linguistic system, they should sort of form in a kind of dynamical process. Now, this is a slightly, crazy idea, right? That you would want to try this. But I think it's only when we see this happening in a group of agents that they arrive at such a communication system that we can really say, yes, we understand something about the origins of categories or the formation of categories, right? So it's a very tough test. Okay, yeah.
Perhaps I missed it, but on your third bullet there, when you say communication system should emerge without human intervention, is this basically, are you saying this is the case for agents, or is this only the case for human populations?
Well, this is what we do in our experiments. This is the goal of our experiment. Okay, of course, in the human population, there's already going to be some sort of system around, right? But we kind of wind back the clock to the very beginning, let's say. It's a bit like studying the origins of life, and you have, of course, the chemistry and everything, and then you want to understand how life would start.
I guess I just don't understand. Maybe you're going to explain this, how humans intervene in the agent population.
Oh, they could intervene by giving examples or by saying, this is red. Okay. But they don't do that. So there are no humans around. We start up the experiment, and then we don't interfere, and then at the end of the day, we come back to see what kind of language has emerged. And so we are like anthropologists trying to figure out this new communication system. Okay? So we do this for real with robots. And, well, the color is not so good, but it's a bit darker. Anyway, so these are the, we use these humanoid robots. They're about as big. And we program them to play games.
Does it actually look like this?
Yeah, they look like this. They play language games. And so one game is that is a naming game. And so the naming game is they are in this world. They walk around. You know, they see some things. They see another one. And then one becomes speaker by random choice. And the speaker will think of an object in that setting that he wants the other one to draw the attention to. And then he's going to use some word or, you know, whatever. It could be an utterance with several words, could be grammar, could be a lexicon. And so he says the word, and then the hearer is going to point. Now, if the speaker agrees that this was the topic he had chosen, he will signal success. And if this is not the case, then he will signal failure, and then he will point to the thing. Okay? So it's like I'm here, and I say, can you give me the dobado? Now, you look at me puzzled because you don't know what I mean. I say, well, this is dobado, right? So at that moment, there is a learning possibility. And maybe I just invented actually a word. I didn't have a word yet for this, but I invented one. And you pick up the word right now, dobado. Okay, we all know it now. Okay, so this is the...
Good robot.
This is the game. So let me show this in action. This is one example. There's a sound which you don't hear very well, but it doesn't matter. So this is a phase where they look around, you know, at the objects in their environment. This takes a while. Now, one of them is the speaker and says a word. Now, the other one is looking around what that might be according to his own lexicon and points to the object. And then the other one looks what is being pointed to and then, you know, says, well, no, this is not what I had in mind. Okay? And he's going to correct by pointing. Right? So he says, it's this one. Okay. So this is one example.
So that's
Now,
an actual movie, not animation.
this is not animation. This is real.
I'm impressed.
Yeah.
Have you established a protocol for what is not the right act or what is a negative act?
Excuse me?
Have you established a protocol or
Yeah.
data into the robot to understand what is a wrong act or a negative act?
Yeah, I'll show the script. Yeah, so this is another game, and partly to show you that it's real, we'll look into the eyes of the robot, okay? So this is what one is seeing, this is what the other one is seeing. And there's, of course, a full-blown vision system on it. You know, what they're trying to do is they're actually, when they look around, this is the field of view, that they're trying to detect objects. They're also trying to detect the position of the other one with respect to themselves, because as you know, in language, perspective is extremely important. So, okay, so they say this, and okay, there's the same sort of thing. This is the 3D modeling going on, actually. And so there's both a top-down process on vision, predicting what the robot is going to see, and then a bottom-up process running on the robot. Let me play it again. You can see that. So otherwise, you cannot do vision actually if you don't couple top-down and bottom-up vision.
So they know what kinds of objects to expect?
No, they don't know. So they start in the beginning of the experiment. They have no idea what objects they're going to encounter. And so, but they see the first scenes. Okay, then they start with an hypothesis of an object. And then they refine that, and every step they refine their model of the object as they go along in time.
What do they know about each other?
Well, there's no identity. So there's no object individual identity. I mean, the only thing they know is the position of the other one.
But they know how to follow points.
They don't?
They know how to follow a point.
Oh, yeah.
And they can tell a robot from a cone, right? They know that a cone is an object and a robot is another
Is a
one of their
robot,
kind.
yes. Yeah. So they do know about other robots. Okay, in that sense, so the robot is a special object in their world.
But the objects which they point to are one of a finite set, right? If you
No.
No?
So it's completely open. The number of agents in the population, the number of objects, they have no clue. When they enter, they don't know.
No, when you say number of objects, it's confusing me a little bit because there are two senses of object. One sense are those red and blue and green cones.
Yeah.
In which case, they enter the room, they look around, and there is an upper bound on the number of objects.
Well,
The
not.
other sense of an object is if you point at something and I'm just observing you, I have no idea whether you mean the leg of the chair, the whole chair, the collection of the room.
Yes.
There's an infinite class of objects that you could possess.
Okay. Yeah. Yes. Yeah. So here we get already in the interesting issues, right? And there are so many. All the problems of philosophy appear in this experiment. But I should say that we do a lot of games. We study a lot of different games. Well, a lot. Let's say half a dozen so far. One game we study is the naming game. And each game makes certain assumptions. Okay, and in the naming game, the assumption is that the possible meanings come from the same domain. For example, the experiment I'm going to talk about is about individuals. So in this naming game, the assumption is that the objects are unique, okay? And so you can give them a name because they are unique. Now, another game we play is for colors. And so then the assumption is that we're talking about color. And then again, it's a name for a color, right? Now, we do other games we call guessing games, where that assumption is not the case. So then you get the Gavagai problem, which is, you point, say, Gavagai, what could it be? The rabbit we're going to have for dinner later, or my favorite pet, or etc., right? So this is not in this game, but we do that too. We also play games where two robots stand in front of each other and they play action games. And so they move their body, and the goal is to evolve a language for talking about the body, which assumes that they relate also image of a behavior with the motor, sensory motor system, the motor system. So we do many kinds of games, but given that there's not that much time, I'm going to focus on one game, and particularly on the categorization part of it. Okay, so this is the kind of stuff that we do. I should also say that we have only a limited number of bodies, but we have a whole infrastructure so that we have agents. We download the agents in the body to play a game, and we upload them. And this way we can have population of many agents using the same bodies, and we can actually teleport, from Paris. We teleport agents to other bodies in the world, and then they play games. Okay, fine. So this is the... Yeah. You might think that, but yeah. Okay, so how do we do all this, right? Okay, now the basic idea is that individuals build up semiotic networks. Individuals, I mean, these are each of these agents. And the networks, they link the sensory experiences to categories and the categories to words. So let's not talk about grammar for a while, okay? Grammar is my favorite subject, but let's keep that for later. Now then, the networks are adjusted by each individual based on success or failure in the language game. And these adjustments, they have to be such that progressively they lead to coordination and thus to the formation of a shared set of categories and the lexicon. So this is the problem that you just talked about we have here. How can a distributed set of agents arrive at a shared lexicon? But they also need to arrive at the categories. We don't put in the categories. Okay, fine. Now this is what such a network looks like in a single agent. Okay, it's just a visualization. So there's going to be, in this case, for the grounded naming game, these are sensory experiences. Then you have prototypes or prototypical views of objects. And these are linked into nodes for the individuals themselves, which then are linked to certain words, right? So you get a network like this. And this network, as I said, is entirely dynamic. So just to show what it looks like, they play one game after another, right? So every time we take two members of the population, they download into the bodies of the robot. They walk around or they do whatever until they create a situation where they can play a language game. And then they play the game. And so at the bottom you find the number of interactions like that. Okay, so it's not every time, by the way, there's only two agents playing. There could be more in parallel, but there's only two so that we can more easily see what is going on. And so this is the network of one agent. And so what you see is that as new experiences come in, new prototypes may be created. And if you look in more detail, you also see that the prototypes themselves are adjusted all the time. So it's a sort of, almost like a living system, right? So you have new links coming in, words being invented, words disappearing, until the population kind of settles on both on the lexicon and on the prototypes and on the set of individuals that they have, right?
So the green things are individuals.
Yeah, these are the nodes for individuals. So this is about individual concepts, right? And so, but a particular individual can have many different prototypical views. So suppose, you see me here, right? And maybe I have strange behavior, and you meet me later tonight, and maybe I'm wearing a wig and, other clothes, and I'll look completely different, right? But still, so that would be another prototypical view which you see then of me, but I'm the same individual, right? So it's not the case that every individual always looks exactly the same. Yeah.
So I'm just wondering, is confusion possible in this prototype network? Because up in there, the yellow prototype nodes, you have examples where there's a red one. So
Yeah.
I wonder.
Yeah, sure. Now, the color coding, maybe this is maybe more orange here on my thing. But sure, there's confusion all the time. And so one of the big problems, as we will see, is not just to learn the prototypes, okay, as a continuous interaction, in fact, to adopt but to learn also which individuals there are, because that's not so obvious. Okay.
What happens to the system that's confused?
What happens? If the system, if an agent is confused, the game will fail. But the failing game is an opportunity for learning, right?
Systematics don't break down?
No, that's the whole purpose, is to invent the dynamics, or to create a dynamics among those agents so that they converge towards a shared system, so that communication is successful, right? But they do it in a distributed way. Okay, so this is the network, the semiotic network. And so I'm going to explain a bit how these different steps, how the network is built and how it's adjusted. And so let me start with the, obviously there are lots of challenges here, right? In order to do such an experiment. There's a lot of challenges in robotics. We need the scripts for playing the game. There are lots of things, like maybe you didn't see it, but there's these tags attached to walls and to other objects, which we're using actually for estimating positions of one object with respect to another object. Then there's also the whole issue of pointing, and how do you detect if you point within your own reference frame, but then the other object has to do a perspective transformation, in order to detect where it's going to be. So there's a huge number of issues like that, which all have to do, in fact, which you don't realize if you just think about agents and direct meaning transfer and that everybody sees the same thing. No, if you do these experiments, you are confronted with reality where you see things from different perspectives. We never see the same thing, right? But I'm not going to talk much about this. I'm also not going to talk about the visual processing. This is more or less what you expect. There's a sort of foreground, background distinction being made. There are features being extracted, color dimensions. The distance is estimated from the robot to the object, size of the object. You can have as many features as you want, actually. And then there's the top-down prediction, as I said, so that you can identify objects. And this is an example of what we are doing, which is that, there's a setup, and then often I walk in and I change the scene before the eyes of the robots. So I take a block, this one here, and I turn it, you see. And the important thing is that the visual appearance of that particular object, this one, is going to change. Now it was a tall object, and now it's on the ground and all that, right? So we play these kinds of games with the object looking, which is I don't have a good example here. Maybe this one. It's like I have two here, right? So now I do this magic trick, right? And I do this. And is it the same? No, you saw. But you see, this is the kind of stuff that we are doing. Okay.
So do you consider the same when it's like this and like this?
Yeah, they track the object. So they are able to track movements of objects and changes in object, and so they can see that it's the same, right? This one. So they have anchors into objects that they can see this persistence.
If you put like a cube and a ball, so if they're far apart, I guess they see them as two different objects.
Yeah.
If you put them together, are they programmed somehow to?
No, if they before saw them apart, and then you put them in front of each other, they will keep.
How about if they're introduced to them?
Yeah, if they're in the beginning, they're together, then it will be viewed as one object. And then you take them apart, these are two objects. These are some of the changes in the network, right? That the agents.
They're able to make this change.
Yeah.
And the object constancy, is it exemplar-based or is it rule-based, or what can you say anything about that?
Yeah, the object constancy here is because of the tracking. So
They have a series of exemplars in their
No.
memory that they do a comparison to, or
No.
template?
No, you could say they start from the first, they see something, and then they see different segments, okay, which could be together, two things together, which we would see as different, but anyway, they are together. And then they predict what is going to be in the next setting. So if the segment doesn't move, it's the same. But if it starts to move and it's not a dramatic thing like it appears and then it suddenly disappears, that kind of thing, and then it reappears, it wouldn't know it's the same object. Yeah?
How long does it take until the object is identified until?
Oh, this is all like in the clip. This is real time.
And then does it automatically issue it a number or name right when it identifies?
No, that's coming. Yeah. We use, by the way, on the robot itself are several processors, some of them specifically for image processing. And you don't see it, but we use 8 computers behind the scenes to also have additional computing power and record everything as it is going. Okay, I emphasize again that speaker and hearer never see the same thing, right? This is for a certain scene. This, by the way, the size here gives the width of the object, the size of the circle. And this gives an idea of the colors. And these are some of the real values here. And this is the differences between the values between the two agents. So that's the real problem of categorization and communication. how on earth can you communicate, when the world is so different from both perspectives? Okay, so now we come to the real thing, the categorization and the lexicon lookup. Let's start with the lexicon. And actually, we've done a lot of work, not just us, but many other people on the naming game, which is just about how do you develop a self-organize a lexicon between objects and names. And the idea is very simple. We use a bidirectional associative memory, like the one that Costco, for example, studied with lateral inhibition. So, which is that when you don't have a word for some individual, you create one, just random. And you start with an initial score. And of course, when there's already somebody else use the word, okay, and you're a hearer, then you associate that word with that individual. So you can have more than one. And now all of these are scored like in connectionist networks. And so you increase the score. You take the one with the highest weight if you have to say something, right? So if you have to express or name this individual, you take the one with the highest score. And as a listener also, you take the interpretation with the highest score. Now, if the game is successful, you increase the score and you decrease the score of the competitors. And if the game is a failure, you also decrease the score. So it's a sort of well-known, simple model. But this is enough to get you the things like this. This is for 10 agents, 10 objects, 2,000 games. So we always plot on this axis the number of games. But there's only 2 agents playing for every interaction, right? And so here we show the size of the lexicon is in blue, and communicative success is in red. And what you see in the beginning is a phase of invention and adoption, because these agents are developing something this one. And then, there's a phase of alignment. They align to each other with this lateral inhibition dynamics. And so you see that they get to an optimal lexicon of 10 names for 10 objects. And it goes very quickly. It's not something you have to think about ages. So there's no fitness here. There's no transmission from one generation to another. This is just a population playing the naming game with these dynamics and arriving at a system. Yeah.
I was wondering how the number of games you need to converge to success, communicative success, changes as you vary the number of agents and objects.
That's a very good question to this, because Andrea, who is there, wrote his PhD thesis about it. So, do you want to respond?
Yeah, well, in a simplified model, we talked about this later. It's n, where n is the population size, to the 1.5 to reach convergence in a case of homogeneous mixing, so without network. And it's interesting because in the naming game, at least in the simplified model I will tell you about, this conversion time, the scaling of this conversion time depends on the number of words in the system. So it goes from n log n, when there are only 2 competing standings, to n to the 1.5 log n, when you have a number of conventions scaling as a population size.
Yeah. There's a lot of work and proofs also of convergence and other things about the naming game. Okay. Now, in this case, the previous graph was when we already gave actually the number of objects. The agents know the number of objects. So the categories are already shared, you could say, which is not the case in this experiment. So this is from a theoretical experiment, if you want, simulation. Now, this is from the real experiment, which is very similar. You see the lexicon size, and you see that there are synonyms and there are homonyms, unavoidably. And you get synonyms because, as I said, agents may invent different words for a particular meaning, not knowing that there's already another one. But then you get this damping of synonymy. But there's also homonyms here, unavoidably, Now, homonyms could be because you invented a word and accidentally you invented the same but for a different meaning. But that probability is very low. But here you have also the issue that the prototypes are not shared. So, you know, you could, the red one is one agent and the black one is another agent. And so they get into communication situations where it turns out that they get homonymy, that means different meanings for the same word, you know, because they had one and another one had one, and etc. Okay, but you see that there's kind of the same, okay.
So the interaction is that every agent talks to every other agent? Or
Well, no, they are picked randomly out of the population. Every turn, 2 agents are picked. But it's totally mixed. There's no social network. There could be one, and it has been studied by Dallasta and other people, you know. But in this case, it's totally homogeneous. Okay, so this is about this part. Now, what about this part? Well, this is sort of the idea of the way we do categorization here is with prototypes. Now, you can do it with other ways. Now, one of the big points that we discovered is that which mechanism of categorization you use doesn't matter that much. I mean, what matters is the overall dynamics, how it's pulled together into a complete system. And so here it's with prototypes, which means that you start the beginning, the seed of a prototype is just a specific sensory experience. And then you adjust it. You know, every time you see it, you adjust it slightly to be closer to that particular sensory experience. And so I have to go a little bit quickly here. So this is a kind of example of this adjustment over time of the sensory experience to be closer. Now, another thing that a prototype has is a score, how well it is doing in the overall game, right, in the communication system. And so you can have prototypes which are created, but then they sort of, you know, either they have success for a while or they will drop down. And the score of the prototype is related, as I say, to the success in the language game. So this is the way that there's a coupling between the language game and the categorization system, you know, because you want them to co-evolve. Okay, now let's say something about this part here. How do you know that a particular prototype is a view of one individual? And here there's no real foolproof method. I mean, even with individuals, right, you can have a mistake that you think this is this person, it's actually this person. And I used to have, I still have 2 friends, and they are twins. Now, I don't know whether you ever been with twins, but we were sitting at the breakfast table. I was talking to one, you know, she walks out, another one comes in, and you don't know. I mean, this is a very disturbing experience. But they know this, and they all the time they say, well, I'm not Patricia, you know, this is the other one, or they help you in this. But first, quite solid heuristic is that if objects are appearing in the same scene, then they're pretty different. So if the 2 twins walk in, okay, there are 2, right? So that's the first heuristic we use to create new prototypes. Because if the individuals, you know, if both of them would be matching with the same prototype, you know that your prototypes are not sufficiently fine-grained, right? So you create, this is one step. And if you do that already, you get this kind of result. This is the communicative success. Okay, so that goes up. After 5,000 games, they basically get it. So they don't know how many objects there are. They don't know, they have never seen the objects, right? And you see, this is the lexicon. The problem is that the number of prototypical views and the number of individuals is equal, which means actually these agents are naming prototypes rather than individuals. Okay, so they see, for example, the object up, standing up, and then they see one stand down, but they don't know that this is the same. Okay, so they have two different names for that particular object, one lying down and one standing up. So then another heuristic is that if objects are named the same, then, well, they refer to the same individual, right? So the bell door rings and somebody is there, you know, and you think you never saw this person before, right? Say, well, you know, it's me, Martha, or something, right? Oh, yes. So the name, and we have this in our agents, this is a particular scene where, let's say, the other robots call this Wotufe, and then there's a scene here where the other robot calls this also Wotufe. Well, this is then an occasion for the robot to learn, you know, that the semiotic network needs to be restructured, and that those two, at least for that person, are the same object. Now another heuristic, and then you get this, so the number of individuals is decreasing. And another heuristic is this tracking over time. So if you see that you know, you see the object up, then you see it lying down, and you see the time, okay, then again you can reorganize your network. So it was like this. This is for this case. Here it's up, here it's down. You know, you can reorganize that. It's the same individual, right? And then you get this, which is that, I mean, we put in 10 individuals, so we know that this is what the system should converge to. And so you see that this is now happening. Yeah?
Once you identify the new pattern, how long is the response time? A lot quicker?
The response, you mean in a game?
Yeah.
But in the game, the response time is very fast. I mean, you have to do the computing, of course, but you know, the systems that we're talking about here don't take much computing time.
Where does most of the computing time come in when?
It's in the vision system. The vision system soaks up 90% of computing time for this. You know, the networks and all of this is not. Now, of course, when you do grammar, things start to change, right? When you have explosions of possibilities, but
Without relocating an object, can the vision?
no, it would be the same. I mean, you have to keep modeling the world all the time, projecting it, do the segmentation, you know, do feature extraction, all of that. Okay, so I hope to have shown you how we do this. You know, and the invisible hand is really this a positive feedback loop in the system, in the sense that if a word has success in communication, then the score goes up, and the others go down. You know, and after a while, there's a winner take all, right? So this is what this is doing, and it's also for the categories. And so these other things are also illustrated in this experiment. So I see that my time is running here. I think it's important to see the difference with other paradigms. And one paradigm which is very interesting is the iterated learning one. But in this case, there is it's not a parent-child kind of system, right? It's peer-to-peer. And the problem of category formation, language formation is viewed not as an induction problem with learners going from one generation to the next, but as a coordination problem in a population of agents. So this is a very important thing. And most people say, but you know, this is not how language works, right? But I can tell you that the same mechanism, we don't have to add anything to get transmission. And this is an experiment. This is actually a follow-up. Before that, we had a population of 10 agents or 20, whatever, that already created a system. And then we throw in a new agent who knows nothing, doesn't know the lexicon, doesn't know the conceptual repertoire, but using the same mechanisms. This agent very quickly, you see after a few hundred or 1,000 interactions, picks up the system in the population, the lexicon that is there, and also learns about the number of objects and the number of prototypes that are in this thing. So in my view, when we explain how concepts and language form bottom up, then the acquisition is solved as well. It's just a part of it. Yeah.
Have you attempted to mix two independently evolved populations that have their own languages?
Right. And then mix them. Yeah.
Mix them?
Yes. And then it depends on probability, size of group, and probability of interaction, in which way it's going to go, whether one will become dominant and the other one. Okay, 5 minutes, okay. Well, I'm sorry to talk so much. So we did many other experiments. One is the Mondrian experiment, Mondrian, the painter, where we do with colors. And it's the same idea, the sensory experiences, but then linked to prototypes of colors, and then also to lexicon, the same mechanisms. Now, you don't have individual nodes here, but it's actually the same sort of dynamics, and we can, this is in the BBS paper, where we actually use the same sort of representations that have been used traditionally in the color literature to show how color systems can emerge in this kind of thing. And so you see prototypes and you see the region around them. This is with radial basis function networks as the categorizers. But it's the same idea and the same kind of result. And also we've done experiments where we let the agents do category formation. So it's still a discrimination game. They have to discriminate different colors, but they don't talk. And then one where they actually use language. And so language is a way to help coordinate the categories in the population. We also did, it's a pity with experiments with these eyeball robots, where they pay attention to a ball and then we move the ball and they track the ball and then they describe to each other the trajectories that they see. So they say, for example, the ball rolled from my left to your right. Okay, and this is an experiment about spatial language and about perspective reversal and all of those things. And that's, of course, another talk. As I said, we're also doing the experiments in body language, and so how body image forms in relation to partly guided by language and making movements of the body. So I think I had some slides about grammar, but maybe I should just do my conclusions before the chairman gets nervous. So I think I'm not making any claims about human categorization, but at least with these models, they show that categories can form based on this constructivist principle. Okay, it's not inductive learning. You don't get a large sequence of data from which you try to generalize. It's the categories are constructed because they are needed to make a distinction, right? And then the second thing is that you have this coordination process. And the coordination process of the language, I mean, is a way in which the agents can get information because they don't have any telepathy. There's no top-down design category, so they cannot know in any other way apart from language in these experiments how to coordinate their categories, right? But it is an effective way to coordinate categories. And the other thing is that it's not that we first do category formation and then we do the lexicon. No, we do everything at the same time. And so the two co-evolve and they shape each other. And this is actually the only way to do it. Because if you let individual agents evolve their own categories, and then they say, okay, now talk to each other, they will have different categories. So the coordination has to go on at the same time. Now, I'm not saying that symbolic communication is the only way. Okay, you can have coordination of categories with any cooperative task, I think. But it's just that symbolic communication is just one of those ways that you can coordinate them. Okay.
If you had had another 3 minutes to talk about grammar, what would you have said?
3 minutes. Am I allowed?
Yes.
Okay. So what I would have said is, first of all, that what is crucial about grammar, in my opinion, is not so much the form, like the word order and all this, but it's that there's a categorization system hidden in the language, right? Semantic categories, syntactic categories. So the problem of the evolution of categories, of psychological categories, is here also, very much. And of course, well, I guess, so you in the previous experiment, you have this kind of thing: sensory motor, then color category, space category, and then names, words for them. So what we need to do, if we go to grammar, is we have an intermediary system of grammatical categories, semantic roles, syntactic roles, a huge number, right? And they form networks also. For example, in expression of object-event relations, you might categorize something as agent, which is then expressed as nominative with a certain marker. And so you get a network which is as dynamic as the networks that I showed you, which competing with each other for being the, let's say, the category. I mean, there's competition for a particular object-event relation, maybe one way of categorizing it. There's one way of expressing it. So all of this is also this kind of network. And of course, it's not a single line like that, because the different roles are put together into, you could call it the schemas for, and so in construction grammar, you would have 3 semantic roles mapping onto 3 syntactic roles, right? And so it's not just individual links, but it's these kinds of patterns that are linked to each other in the network. And so we've been doing a lot of work on how we could see the emergence of grammar using also language games and doing, well, I can't, I think my 3 minutes are almost up. But what I would like to say, though, is what we're trying to simulate, in fact, are grammaticalization processes. And the grammaticalization is typically that if you want to say something in a language, and in this case, future, typically you can do it by, if you don't have a grammatical way or you don't have direct words for it, you can do it by using more than one word, right? So apparently in Latin, in order to have future, they started using the verb habeo for have. And that then is typically, there's erosion, there's contraction, there's bleaching, and all these processes then are giving you some system like here. This is the French future expression. So, there's lots of processes going on in evolution of grammar. I mean, but they all have to do with solving communication problems, making things quicker, and so on. So I don't particularly buy this model of, let's say, that the change is happening in the transmission from parent to child, but rather in the population, that they use various ways to solve their problems, right? And then as part of it, like this periphrasis is where you start using this, you generalize it, and then it propagates in the population and all those kind of things. So that's what we are trying to do in our grammar work. I'm sorry, I had my 3 minutes.
Last until another 5 minutes.
Oh, but there may be other, well, then I will say one more thing, which is that, so the way we do this is that the speaker, when he's formulating a multi-word utterance or a sentence, will actually first re-enter the sentence for himself. So he's going to use himself as a model of the here in order to figure out, for example, is there uncertainty, is there ambiguity, is there a combinatorial explosion here? And then the speaker will add more form. For example, you could start with a language without any word order. And then you get into the problem of ambiguity of, let's say, event-object relations, so or predicate-argument structure. Now, so the speaker will detect that there's potential of misunderstanding in the here, and will then extend his grammar, okay, to deal with that problem, and then say it. And the here will first, do the hard work of trying to figure it out, even with partial, even if he doesn't understand a few of the words or he doesn't know that there is word order. He just does his best with what he gets, and then say, well, okay, this is the meaning, and maybe they play the game, so they get feedback whether they correctly understood it. And based on all of that, the here will say, okay, now what could this extra information in this sentence mean? Okay, and then, for example, for avoiding a combinatorial explosion or for marking a certain event-object relation. So these are examples of experiments where we increase the complexity over time. This is still the number of games. We increase the complexity of the meanings that they are expressing. And this begins with a purely lexical language, no grammar at all. And you see that they build up the lexicon, they get success, but then success is tumbling down. Lexicon is beginning to increase because they don't have a way to, there are ambiguities. And so then this is a second step where they start to build the grammar. So this is the percentage of sentences that have grammatical structure in it. But at the same time, there's a search is beginning to increase, in parsing. And so then they add more. Here they have the ability to actually see search, repair it, and dampen the search. And so there's grammar here. There's a lexicon that stabilizes. This is communicative success. So these are the kinds of things we do for grammar. Well, I'm sorry that it's all a bit hand waving, but. Okay.